Hi everybody, welcome, great to see you. Today I'm going to start Unit 10, Kinetics and Equilibrium. So let's jump right in with our first lesson, 10.1, how do we apply the kinetic molecular theory? I'll go over the question of the day, I'll show you a video demo, and then the lesson is about the combined gas law. And there's an optional practice homework at the end for you to practice your skills, and I'll post all the answers on the next video so you can see how it went for you. All right, so our question of the day, why do you think balloons rise when they are heated? And what do you think makes a reaction go? I'm gonna let you just pause the video and think about both of these questions. The first one has to do with today's lesson, and the second one has to do with this whole unit, kinetics and equilibrium. Great, so here we are coming up on our last unit of chemistry, kinetics and equilibrium. We started off with the physical nature of matter, then we studied the most basic unit of matter, the atom. Then we looked at the interactions between atoms when we studied different types of bonding. Then we looked at how bonds are broken and formed when we studied patterns and chemical reactions. Then in second semester, we zoomed in on the nucleus to study nuclear chemistry. Then we looked at patterns found on the periodic table. Then in stoichiometry, we quantified chemical reactions. And then we used that in solutions to learn how to make solutions of different concentrations. And we learned about their characteristics. Then in acids and bases, we looked at some special solutions that had really interesting and colorful properties. And in our last unit of the year, we're looking at how can you manipulate chemical reactions. The two bonus topics we didn't get to, oxidation reduction, we'll get to in AP chemistry, and organic chemistry we'll probably skip, or we might just do it for a couple days just for fun. All right, so for this demo, I would love to show you this in the classroom, but you can also do it at home. You're gonna take a can, fill it with water, heat it on the stove, and then once the water in the regular pop can starts steaming a little bit, use tongs to flip it over in a bowl of cool water and see what happens. I'm gonna show you what happens and ask you before the demo, are you rooting for the can or the atmosphere? Okay, we'll take a look, see what happens, and I'm gonna skip to that spot.
So, medium high heat, place your can with the water in it in the center of the burner. Leave it there until you see water vapor coming out of the top. Now quickly dunk your can into the water.
Okay, so clearly the atmosphere wins in that battle. So if you could pause the video, think about why do you think this happens? And you can share with a friend if you have one nearby that you're doing this with. Okay, so here's what happened. We had some water down here in the can. Draw it in. Okay, what happens? And then we had air up here. What happens when we heat up the water? Well, a bunch of the water molecules turned into water vapor, and they pushed out the air, and it just filled it with gaseous water molecules. All right, now then when you flip over the can, all of a sudden it gets sealed off at the top and instantly cooled. What happens to water vapor when it cools? That's right, it turns back into water. So these guys turn back into water, whoop. Now they're not exerting that pressure anymore. So all of a sudden, the pressure on the outside of the can, the regular air pressure, is way stronger than the pressure on the inside of the can, which is really small now because all those little water molecules turned back into water, liquid water. Okay, so that's some of the stuff we're going to be studying in today's lesson as we look at some of the properties of gases to study kinetics and equilibrium. So today's aim is 10.1. How do we apply the kinetic molecular theory? Okay, so KMT, Kinetic Molecular Theory. This is basically the way we imagine gases and how we can explain their behavior. So we picture, first of all, that the particles are just bouncing around in constant random motion. It's not like all of them are suddenly going one way or the other direction. It's not organized. Secondly, we acknowledge that they collide with each other, but we imagine that when they collide, they either react and form something new, or they just bounce off each other and keep going. And finally, we say they have no intermolecular forces. Now you might be thinking, wait a second, what? No intermolecular forces? That doesn't make any sense, right? Because if they had no intermolecular forces, what would keep this still a gas, right? Otherwise, wouldn't the particles just float away and not be a substance anymore? You're right. The idea of kinetic molecular theory is that the intermolecular forces are so weak that we ignore their effect. If they were strong, then they might slow the molecules down when they got close to each other, or cause them to stick together and turn into a liquid, but we're picturing just particles bouncing all around at random. I like to think of this. You ever see these ads on TV when they're like, and the winning numbers are, and they pull them out? You can picture the particles bouncing around at random like those little ping pong ball things in the lottery. So this is what we call an ideal gas. We're just saying it's one that behaves like we're describing in the kinetic molecular theory. Real gases sometimes do kind of have intermolecular forces, and maybe the particles do kind of slow down and stick together, but when they're ideal, they don't. So real gases often behave just like we predict ideal gases do, and especially when they're at low pressure and high temperature. At low pressure, they're not squished. At low pressure, they're allowed to sort of, be free. So they're not necessarily going to squish and stick together. And at high temperature, the particles have lots of energy, so they can bounce each other and keep going, as opposed to if they were low energy, maybe they'd stick together when they collide. So they act most like we imagine a gas acts when they're at low pressure and high temperature. So, which of these two guys, gas volume 1 or gas volume 2, at a constant temperature, which one would be more ideal? That's right, volume 1, because the particles have less pressure on them. All right, so we can quantify and qualify the relationships found in gases with some of these graphs. So taking a look at this first graph of volume versus pressure, what would you say is the relationship for a gas? That's right, inverse. As volume increases, pressure decreases, or as pressure increases, volume decreases. Picture a balloon, right? If you squeeze the balloon, increase the pressure, it gets smaller. Tiny little balloon is high pressure, low pressure balloon would be really big. So the relationship between volume and pressure are inversely related. How about the relationship between volume and temperature? That's right, it's a linear relationship or direct relationship. Or in other words, as temperature increases, so does volume. Think of your balloon again, right? You know, if you heat up a balloon, it gets bigger. Here are some examples. Breathing. Here's how breathing works. Say you want to take a breath. How do you get the air in you? Well, you have to decrease the pressure inside your body so that the pressure is greater outside than inside, so the air goes in. How do you decrease the pressure inside? Well, you contract your diaphragm, which means you make the volume bigger. So you make the volume bigger inside. Now it's low pressure, so now the air goes in. My second example here is with volume and temperature, And this is the question of the day. How do hot air balloons work? Why do they rise? Well, hot air balloons are hot for a reason. When the air is hot, now those particles have a bunch of energy, so they spread out, or in other words, the volume gets really big when the temperature goes up. And if the volume is really big, now the particles are more spread out. Now they're less dense, same mass but a bigger volume, less dense than the air around it, and so it floats. Cool. Okay, so pressure and volume are inversely related. As one increases, the other decreases. And pressure and volume actually both are directly related to temperature. As temperature increases, so does pressure and volume. Okay, so if you put these together, you get our last equation of the school year, the combined gas law. Pretty simple to use. P1 V1 over T1 equals P2 V2 over T2. P stands for pressure, V for volume, and T for temperature, specifically in kelvins. This last equation is on the back of your reference table. It's right here. Now you have learned them all. Congratulations. We kind of skipped density because that's supposed to be something hopefully you already knew about, but don't worry if you don't know it. It's okay. Too simple. But the rest of these now we've learned. Yay! So let's take a little look at how you measure each of the variables in the equation. So we always use kelvins for measuring temperature. Why can't we use Celsius? Celsius is a nice unit, you say. I agree. It's based on water, so handy. Okay, but what happens if you have a gas that is at freezing, 0 degrees Celsius? That'd be a problem in an equation. It would be 0. You can't divide by 0, then you get an unknown number. So instead of Celsius, we use kelvins because kelvins are always a big number. You'll never worry about having 0 kelvins for your temperature. And if you forget, there's an equation on the back of your reference tables we used a long time ago to convert between Celsius and kelvins. It's real simple. You just always add 273. Okay, measuring pressure. This one's kind of annoying, I guess, in that you can measure it so many ways. You can measure pressure in torr, or in millimeters of mercury, or in kilopascals, or atmospheres. Those are all just like the way we use it in science. There's also other ways we measure pressure in other fields. But the two most important for now, for this equation, are atmospheres and torr. Recall that at STP, standard temperature and pressure equals 1 atmosphere or 101.3 kilopascals. That's the same, and you can add this, you can write this in on your own reference tables. That's the same as 760 torr or 760 millimeters of mercury. Just a whole bunch of different units that all measure the same thing. Pressure. Okay, and then volume. How do we measure volume? Usually we use liters. You guys are familiar with those, and I just wanted to remind you of this fact from stoichiometry that comes into play again, which is 1 mole of any gas will always have the same volume, 22.4 liters, at STP, no matter the gas. Such a handy factoid. Any gas will have that same volume, 22.4 liters, at STP. 1 mole of that gas. Okay, so let's do some examples. Example 1. What volume will a gas occupy if the pressure on 244 centimeters cubed of gas at 4 atmospheres is increased to 6 atmospheres, assuming the temperature remains constant? All right, so we're definitely going to want our handy new equation. P1 V1 over T1 equals P2 V2 over T2. All right, and then what I like to do is identify all the numbers given as one of the variables. So this guy, 244 centimeters cubed, this centimeters cubed is an amount of space, so that's a volume. And it says, what volume will a gas occupy if the pressure on this gas? So this sounds like an initial condition, so I'll call it volume 1. Okay, this number here, atmospheres, that's a pressure. So that's P1. Now it says increased to 6 atmospheres. So that means pressure 2. And then it says assume temperature remains constant. That means it doesn't matter what number temperature is. We can call it 1 since it doesn't change and just take it out of the equation. And then the question says, what volume will the gas occupy? So they're saying, what will the volume be, or what is V2? So we'll just put in numbers for everything else. Okay, so P1, V1 equals P2 times V2. Since we're solving for V2, I'm going to divide both sides by P2 to get V2 by itself on one side of the equation. Okay, so there's my rearranged equation, and now I'll just fill in numbers for everything. So pressure 1 is 4. Volume 1 is 244 centimeters cubed. And pressure 2 is 6 atmospheres. All right, so the unit atmosphere will cancel. And we get 4 times 244 over 6 is 162.666666. So looks like we have 2 sig figs. So we'll say that's 160. And it looks like our unit we have left is centimeters cubed. Cool. All right, let's make sure that that makes sense. Okay, so the pressure was originally at 4 atmospheres and it got higher. Temperature was constant. So does it make sense that when the pressure was increased, the gas got smaller in volume? Yes, because pressure and volume are inversely related. When you increase pressure, volume decreases. Great. Okay, example 2. If 1 mole of oxygen gas is at STP, what volume will the gas occupy? The temperature is raised to 75 degrees Celsius and the pressure is increased to 945 torr. All right, I'm going to start with our equation again. Sounds like the perfect time to use combined gas law because they're giving us some pressures, volumes, etc., and asking for one of those things. Okay, so let's start with this number, 75. That's clearly a temperature. And it says raised to, so that means this is temperature 2. Currently, it's in Celsius. I want to switch that to kelvins real quick. So that's where you just take Celsius, add 273. So 75 plus 273, you probably did that in your head already. 348 kelvins. Okay, so that's our temperature 2. This number here, so that's this guy, this temperature 2. This guy here, 945 torr. Torr measures pressure. So that looks like increased 2. That means it's a second pressure. Okay, so where the heck are all of our other numbers? We need some more numbers, right? Well, a lot of them are contained in this simple phrase, standard temperature and pressure. Those are on the front of your reference table. This means T1 is standard temperature, which is 273 K. And this means pressure 1 is standard pressure, which is 1 atmosphere. Since this is in torr, I'm going to write this in torr also. 1 atmosphere is the same as 760 torr. And that's a number you can just write into your reference tables. You don't have to memorize. All right, they also said we have 1 mole at STP. 1 mole of any gas, doesn't matter if it's oxygen or anything else, always has the same volume at STP. So that means volume 1 is 22.4 liters. Okay, so now we have volume 1, pressure 1, temperature 1, temperature 2, pressure 2, and they said what volume will the gas occupy? So we're solving again for V2. So to get volume by itself on one side of the equal sign, you're going to multiply both sides by T2. And divide both sides by P2 to get rid of it. So here's my rearranged equation. So I'll just put in all these numbers then. Pressure 1 is 760 torr. Volume 1 is 22.4 liters. Temperature 2, 348 kelvins. Temperature 1, 273, standard temperature. And then pressure 2 is 945 torr. Ooh, that's a lot. Okay, I'm gonna cross off the units and cancel. So we'll just be left with liters. So we've got 760 times 22.4 times 348 divided by, parentheses, 273 times 945, end parentheses. 22.96393. Looks like we have 3 significant figures, so we'll call that 23.0 liters. Cool, so let's make sure this makes sense. It started off at 22.4 liters and it increased very slightly to 23.0 liters. Why didn't it really change? Well, let's see, we heated it up by 75 degrees Celsius. That should make it bigger. But then we also increased the pressure, so that should make it smaller. So it kind of makes sense that it ended up being about the same size it started. Great. Example 3. Which sample at STP has the same number of molecules as 5 liters of nitrogen dioxide gas at STP? Okay, well, all of the answer choices are different units, but note that all of them are gases. So is it more important that we have the same number of grams, liters, 5 moles, or 5 times 10 to the 23 molecules? Well, to make sure that we have the same number of moles as 5 liters of NO2, we want to have the same volume, because we know 1 mole of any gas, no matter the gas, always has the same volume. So if they have the same volume, they have the same moles. So that'll be this one, 5 liters of CH4. And our last example, at constant temperature, the relationship between volume of a gas and its pressure is ding, 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 pressure times volume. That's from the equation, right? PV over T. Great. That's it, you guys. 23, homework 23 here is optional. I put it in the back of the PowerPoint. So you can either pause this video and try the questions or check it out in the PowerPoint. And I'll post the answers in the next video. Thanks for hanging in there. See you next time.